Okay, Avery, I wanted to include this. This slide is not mine, but I just thought I would have the title be what we were talking about. I just wanted to remind you what I believe they are, and that is one agrees with observed data. Okay. So remember, if you do an experiment and you collect data, the theory you make should agree with observed data. I'm not saying this stuff isn't great. I kind of like general. I kind of like simple. I kind of like clear. These all seem like the same thing. Beautiful and elegant. Who doesn't want that? Okay, number two, remember I can fly, right? So few assumptions. This is a sad little writing thing, isn't it? Few assumptions. And think about it. The more times you ask someone to believe something without proof, the weaker the theory is. So I'm just gonna do this, and then there's a P, and then I'm gonna stop. Okay, and then the third, remember, makes predictions, right? And that was big to your teacher too. Good theories predict. Think about how Neptune was discovered. The telescope folks couldn't see it, but the math folks, their math wasn't coming out right. And so they said, hey, if this other planet were here, then the math would come out right. And so it predicted the existence of a new planet. Remember that Einstein's theory of relativity predicted that time would slow near black holes. He couldn't go there. We still haven't been there. But he predicted it, and we've been able to prove now that it's true. So, theories. Last thing I would say, models. We make models so that we can make things simpler, so that we can test things where we aren't present, like at the surface of black holes, or if I just wanted to have a problem with an Indy race car. I can't bring that in my physics classroom, but I can make a test on a dune buggy that I can travel in the classroom, or a ball rolling fast. And if I can make a model that will apply to all things with this type of motion, then I can use it to solve a problem that I can't bring into the lab.